Let's say that we're looking to borrow $50, so we can say that our principal is $50. We're going to borrow it for 3 years. So our time, let's say t in years, is 3. And let's say we're not going to just compound per year. We're going to compound 4 times a year, or every 3 months. And let's say that our interest rate, if we were only compound once per year, it would be 10%. But since we're going to compound 4 times a year, we're going to see in an expression, we're going to divide this by 4 to see how much we compound each period. So 10% is the same thing as 0.10. So let's write an expression. I encourage you actually to pause this video and try to write an expression for the amount that you would have to pay back if you were to do this. If you were to borrow $50 over 3 years, compounding 4 times a year, each period you would be compounding 10% divided by 4%. How much would you have to pay back in 3 years? Let's write it out. $50, that's your principal, and you're going to multiply that. So you could compound it. Each time, each period, each of these 3 times 4 periods, you have 3 years, each of them divided into 4 sections, so you're going to have 12 periods. So each of them you're going to compound by 1 plus this r, so I'll write that as a decimal, 0.10 divided by the number of times you're compounding per year to the well, you'd be raising it to the nth power if this was only over a year. So there's 4 periods, and you'd raise it to the 4th power if it was only a year. But this is 3 years, so you're going to be doing this 3 times 4. You're going to have 4 periods 3 times. So let me write this. So it's going to be 4. Actually, let me write, instead of n right over here, let me write the 4 so you see all the numbers. So you're going to do this 4 times 3 to the 4 times 3 power. And we could even, well, I encourage you, if you want, you could pause the video and you can use your calculator to actually calculate what that is. But the whole point of this is just to use real numbers to see why this actually makes sense. This is your principal. Each time you're going to be multiplying that times 1.025, or you're going to be growing it by 2.5%, and you're going to do this 12 times because there's 12 periods, 4 periods per year times 3 years. So this is going to be how much you have to pay back. So if we wanted to write this in a little bit more abstract terms, we could write this as P times 1 plus, and I'll do the close parentheses since it's the same color, R over n to the n times t power. And so you could pick your p, your t's, your n's, and your r, and you could put it here, and that's essentially how much you're going to have to pay back. Now, an interesting thing, and you saw that we had this up here from a previous video where we took the limit as n approaches infinity. Well, let's do the same thing here. Let's think about what that would mean. If we took the limit as n approaches infinity, if we took the limit of this as n approaches infinity, what is this conceptually? Well, we're dividing our year into more and more and more chunks, an infinite number of chunks. So you could really say, well, this would be the case where we're doing continuous compound interest, which is a fascinating concept to me. You're dividing your time period in an infinite number of chunks, and then compounding just an infinitely small extra amount every one of those periods, but you can actually come up with an expression for that. And as we see that this actually doesn't just go unbounded and give us crazy things, that we can actually use this to come up with a formula for continuously compounding interest, which is used heavily in finance and banking and as you can imagine, a bunch of things, and actually many things outside of finance and banking, exponential growth, etc., etc. So let's see if we can actually try to evaluate this thing right over here. Well, the one thing I'm going to do to simplify this is to do a substitution. So I'm going to define a variable. I'm going to define, the whole goal is so I can get it into a form that looks something like this. I'm going to define a variable x. And I'm going to say that x is the reciprocal of r over n, so that I can get a 1 over x right over here. So I'll write that as n over r. X is equal to n over r, or we could write this as n is equal to x times r. N is equal to x times x times r. And if we make that substitution, the limit as n approaches infinity. Well, if we take the limit as x approaches infinity, then n is going to go to infinity as well. Or if n goes to infinity, then x is going to go to infinity as well. R right over here is just a constant term. We're just assuming that that's a given, that n is what we're really seeing what happens as we change it. So we could rewrite this thing right over here. And I'm doing it, I'm not being as super rigorous, but it's really to give you an intuition for where the formula we're about to see comes from. Let's rewrite this as the limit as x approaches infinity. The limit as x approaches infinity. And the limit of some constant times some expression, well, we could take the constant out. So we could say that's going to be p times the limit as x approaches infinity of 1 plus, well, r over n is 1 over x. 1 plus 1 over x, 1 over x, to the, well, n is x times r. N is x times r, so let me write that, to the x times r, r times t power. T power. Well, all of this business is the exact same thing. So let me rewrite this. Let me copy and paste this part right over here. So copy. This is the same thing. This is equal to p times, let me put some parentheses here, times, maybe that's too big, times the limit, so this limit right over here. So if I raise something to the product of these, I'm taking x times r times t, well, that's the same thing as doing this whole thing to the x, and then raising that to the rt power. Rt power. This comes from exponent properties that you might have learned before. These two things are equivalent. I'm doing a couple of steps in the process here, but hopefully this seems really reasonably intuitive for you. I'm really just using the property that the limit as, let's say, x approaches c of f of x to the, let's call it, to the xrt power. This is the same thing as the limit as x approaches c of f of x to the x, and then all of that raised to the rt power. Well, what is this stuff right over here? What is all of this business that's inside the parentheses? Well, we've seen that before. All of that is equal to e. So we can write this, and this is exciting. This is a formula for continuous compounding interest. That if we continuously compound, we're going to have to pay back our principal times e to the rt power. To the rt power. So let's do a concrete example here. If you were to borrow $50 over 3 years, 10% interest, but you're not compounding just 4 times a year. You're going to compound an infinite times per year. You're going to be continuous compounding. So we can see how much you would actually have to pay back. It is going to be 50 times e to the, our rate is 0.1. So let me put some parentheses here, 0.1 times time. So times 3 years. T is in years. We assumed it was in years. And we get, you would have to pay back $67, and if we were to round, $67.49 if you were to round.